June 1941, a British infantry company near Salem, Egypt, watches 6 German Panzer III tanks roll toward their position. The lieutenant orders his anti-tank rifle team forward. 2 men lugging a 55 lb boy rifle that could supposedly punch through armor. They set up, aim at the lead tank's hull at 200 yards and fire. The half-inch tungsten round hits dead center. It leaves a fist-sized dent and ricochets into the sand. The Panzer doesn't even slow down. 4 minutes later, that entire company is either dead or running. This wasn't an isolated incident. This was the standard experience for Allied infantrymen. From 1939 through early 1942, German armor engineering had leapfrogged everything the Allies could carry into battle. The Panzer III came with 50 mm of front armor. The Panzer IV had 80. The Tiger I's, which started appearing in late 1942, rolled into combat with a 100 mm of hardened steel protecting its crew. And Allied foot soldiers had effectively nothing that could stop them. Let's talk about what they did have. The Boy's anti-tank rifle, Britain's main answer to armored vehicles, could penetrate 21 mm of armor at 100 yards under perfect conditions. Perfect conditions meant flat angle, no sloping, the right type of steel. Combat conditions were never perfect. The rifle weighed as much as 2 men's full kit, kicked hard enough to break collarbones, and required 2 soldiers to operate. Most importantly, it couldn't reliably stop anything heavier than a light armored car. By 1941, the Americans had it worse. When the U.S. Army entered the war, their anti-tank rifle was the .50 caliber M2 Browning machine gun. This was the same gun mounted on half-tracks and aircraft. Against a moving Panzer IV, it was about as effective as throwing rocks. Some infantry units carried sticky bombs, devices you were supposed to run up and attach to a tank by hand. The survival rate for soldiers attempting this maneuver was roughly what you'd expect for someone sprinting toward a 30-ton machine gun platform. The British tried the Pat projector infantry anti-tank, which launched a 2 lb bomb using a massive spring. It had an effective range of about 100 yards, required 40 lb of force to, and frequently failed to penetrate even when it hit. One British sergeant in North Africa described it as a drain pipe loaded with hope. The French had the Brandt ML1935 grenade launcher. The Soviets used anti-tank grenades that required soldiers to close within throwing distance 20 to 30 yards from machines bristling with machine guns. Here's what made this situation genuinely terrifying for Allied commanders. Armor doctrine was changing. German tactical philosophy by 1941 centered on combined arms, tanks supported by infantry and artillery all moving together. When a panzer division attacked your position, you couldn't just hide and wait for your own tanks to show up. Your own tanks were probably burning 3 miles back. You needed something a 19-year-old infantryman could carry, aim, and fire before that panzer's machine gunner cut him in half. Something that would actually penetrate the armor and stop the tank. By late 1941, after watching entire divisions crumble under German armored assaults in France, North Africa, and the Soviet Union, Allied war departments were receiving the same desperate message from every theater. Give us something portable that kills tanks or we're going to lose this war, one shattered infantry company at a time. The casualty reports made the math brutally clear. During the Battle of France in 1940, German armor shredded Allied defensive lines specifically because foot soldiers had no effective answer to tanks. The problem wasn't tactics or courage. The problem was physics. Infantrymen were bringing 20 penetration to an 80 armor fight. And that's the situation facing U.S. Army ordnance in early 1942. Fix this problem fast or start explaining to families why their sons died helpless against machines they couldn't scratch. The solution arrived in the form of 2 Army officers standing in a Maryland workshop with a piece of pipe and a terrible idea. Captain Leslie Skinner had spent months working on a handheld rocket grenade, a small explosive projected by a solid fuel motor that a soldier could theoretically throw farther than his arm allowed. The prototype worked barely, but the rocket motor's back blast was enough to blow off the thrower's hand. Not ideal. Lieutenant Edward Oule watched one of Skinner's test rockets fly and asked the obvious question, what if we don't throw it? What if we just launch it from a tube? Skinner looked at him like he'd suggested building a cannon out of cardboard. Then they did the math. A simple steel tube open at both ends would let the rocket motor's exhaust vent backward while the projectile flew forward. The operator would stand behind the tube, aim, fire, and if everything worked, stay alive. They tested the first prototype in May 1942 at the Aberdeen Proving Ground in Maryland. Poole grabbed a piece of pipe from a scrap heap, measured it to match the rocket diameter, and sealed one end with a wooden plug that had a small hole for the electrical firing wire. They mounted it on a crude shoulder stock made from wood and metal fittings. The entire assembly looked like something a mechanic welded together during lunch break, because that's essentially what it was. The first test shot went 60 yards and hit within 10 ft of the aiming point. The second shot went 50 yards and veered 15 ft left. The third shot tumbled end over end and landed 45 wide short. But here's what mattered. The tube didn't explode. The operator didn't die. And the rocket motor generated enough velocity to potentially damage a tank. Army ordnance observers watching from behind sandbags saw exactly what they needed, a portable concept that might actually work. General Gladian Barnes, Chief of Research and Development for Army Ordnance, saw the demonstration and immediately ordered development to continue. By June 1942, they had a designation, the M1 rocket launcher. By July, someone noticed the tube looked like a musical instrument comedian Bob Burns played on radio, a long pipe contraption he called a bazooka. The name stuck faster than official paperwork could prevent it. Now came the problems. The M1 launched a 3.5 lb rocket with a shaped charge warhead designed to penetrate armor. Shaped charges work through a fascinating physics phenomenon. An explosive line with a copper cone focuses the blast into a superheated jet of metal plasma that cuts through steel like a cutting torch. In theory, the M1's warhead could penetrate over 4 in of armor plate in theory. In practice, accuracy was atrocious. At 50 yards point-blank range for tank combat, the rocket might land anywhere within a 20 ft circle. At 100 yards, you were essentially aiming at a general direction and hopping. The problem wasn't the warhead or the motor. The problem was the smooth bore tube. Without anything to stabilize the rocket's flight, tiny variations in motor thrust or wind conditions would send the projectile spinning randomly. Sometimes it flew straight, sometimes it tumbled, sometimes it corkscrewed through the air like a drunk pigeon. Field tests in late 1942 showed the scope of the disaster. Soldiers at Fort Benning fired 200 test shots at stationary tank targets at 75 yards. Hit rate 38%. Against a moving target, hit rates dropped below 20%. Officers watching these tests did grim math. If your bazooka team only hits 1 shot in 5, and you only get 1 shot before that tank's machine gunner kills you, you're not stopping tanks. You're volunteering for suicide missions. By December 1942, Army Ordnance faced a choice. Scrap the bazooka program entirely or fix the accuracy problem before thousands of these useless tubes shipped to soldiers who would trust their lives to them. The proposal landed on Colonel William Crower's desk at Aberdeen Proving Ground in January 1943 like a grenade without a pin. A civilian ordnance consultant named Henry Mohaupt had spent 3 weeks analyzing the bazooka's accuracy failures and concluded the Army was approaching the problem backwards. Instead of trying to perfect the rocket motor or adjust the warhead weight, he suggested they rifle the launch tube, cut spiral grooves inside the smooth bore just like a traditional firearm. Crozier's response, according to meeting minutes, was immediate. Absolutely not. His reasoning seemed sound to everyone in that room. Rifling works by forcing a bullet to spin as it travels down a barrel. The grooves cut into the barrel engage with the bullet's surface, imparting rotational velocity. This gyroscopic spin stabilizes the bullet's flight. But the bazooka wasn't firing a bullet. It was firing a rocket with its own motor still burning. Crozier argued that forcing a rocket to spin while its motor was creating forward thrust would create unpredictable aerodynamic forces. The weapon might become even less accurate, or worse, the rocket could tumble and detonate prematurely. There was another concern that Crozier didn't say out loud, but everyone understood. They'd already manufactured 14,000 M1 bazookas. These weapons were in production at 3 factories. Some were already created for shipment to North Africa. If rifling proved necessary, every single tube would need to be either scrapped or recalled and remanufactured. The cost would run into millions of dollars. The delay would mean troops going into combat, possibly the upcoming Sicily invasion, without adequate anti-tank weapons. Mohaupt pushed back. And this is where the story gets interesting. He wasn't some academic theorist. He was a Swiss-born engineer who'd worked extensively on shape-charge warhead design before the war. He'd helped develop the principles behind the bazooka's penetrating warhead, and he brought data. His calculations showed that the rocket motor's burn time 2 seconds was actually an advantage. If the tube's rifling spun the rocket during that brief acceleration phase, the projectile would maintain stabilized flight for the remaining 2 to 3 seconds of flight time. The spin wouldn't fight the motor thrust. It would complement it. He also pointed out something embarrassing. The Germans were already doing this. Intelligence reports from captured Panzer launchers, Germany's reverse-engineered copy of captured American bazookas, showed the Germans had added rifling to their tubes, and their accuracy was measurably better than the American original. The meeting ended with Crozier denying the proposal. His written rejection cited insufficient testing data and unacceptable modification risk to approved ordnance. In military bureaucracy language, that meant we're not gambling on your theory when we have a working design, even if that design doesn't work very well. Mohaupt had one card left. He knew Captain Skinner from earlier shape-charge development work. Skinner, despite being Army, had a reputation for pushing unconventional solutions. More importantly, Skinner had General Barnes' ear. So Mohaupt did what frustrated engineers have done since engineering was invented. He went around the official channels. Within a week, Skinner had arranged for Mohaupt to brief Barnes directly. The general listened to 15 minutes of explanation about gyroscopic stability, rocket motor physics, and German intelligence reports. Then he made a decision that would reshape American anti-armor doctrine, approve construction of 3 rifled prototypes for comparison testing. If Mohaupt's theory failed, the project dies. If it succeeds, full production modifications begin immediately, regardless of cost. Crozier got overruled by his superior, which made the upcoming test personal. The standard military response to being overruled is to ensure the test conditions make success as difficult as possible. If rifling failed under rigorous testing, Crozier would be proven right. If it succeeded, he'd order the modifications and take credit for thorough verification. Either way, institutional protocol was satisfied. The test date was set for January 28, 1943. Aberdeen Proving Ground. Captured German Panzer IV armor plate. 20 shots with standard smooth-bore bazookas. 20 shots with Mohaupt's rifled prototypes. Everything measured, documented, witnessed. Before we get to that frozen morning at Aberdeen, you need to understand why spinning a rocket would make it punch through 8 in of steel instead of 4. The physics here gets fascinating, and it's not what most people think. First, let's talk about what happens when a shape-charge warhead hits armor. The warhead contains an explosive charge behind a copper cone. Imagine an ice cream cone made of copper point facing backward toward the explosive. When the warhead detonates, the explosive wave collapses that copper cone inward at speeds exceeding 20,000 ft per second. This collapse converts the copper into a superheated jet of metal plasma, a stream so energetic it behaves more like a fluid than a solid. This jet traveling at about Mach 25 impacts the armor and essentially flows through it, creating a narrow but deep penetration channel. Here's the critical part. The jet forms in microseconds, about 20 millionths of a second after detonation. The geometry has to be perfect. If the warhead hits at an angle, even 15 degrees off perpendicular, penetration drops by 30%. At 30 degrees off, you might not penetrate at all. The jet forms but spreads across the armor surface instead of driving through. This is why smooth-bore bazooka accuracy was such a disaster. A rocket tumbling through the air might hit the tank sideways, nose up, or at any random angle. Even when it hit, it often failed to penetrate properly. Now add spin. A rifled tube imparts roughly 2,000 rotations per minute to the rocket as it launches. This rotational velocity creates gyroscopic stability through basic physics. The same principle that keeps a spinning top upright. A spinning object resists changes to its axis of rotation. For the bazooka rocket, this meant once it left the tube pointing at the target, it stayed pointing at the target throughout its flight. No tumbling, no wobbling, no random orientation changes. But Mohaupt understood something deeper. The spin didn't just stabilize the rocket's trajectory. It stabilized the shaped charge jet formation itself. Research from 1941 by Swiss physicist Franz Rudolf Tomc had shown that even microscopic rotation in a shaped charge warhead could affect jet coherence. Too much spin over 10,000 RPM would tear the jet apart through centrifugal force. But moderate spin in the 2,000 to 3,000 RPM range actually helped the jet maintain coherence by evening out tiny imperfections in the copper liner. Think of it like this. An unspun rocket hitting a tank is like throwing a dart while blindfolded. You might hit, and even if you do hit, the dart might strike at a weird angle. A spun rocket is like throwing a dart while sighted with the dart itself engineered to correct its flight path. You hit where you aim and you hit point first. The math supported this. Mohaupt's calculations predicted rifled rockets would maintain nose-forward orientation within 2 degrees of their launch axis over a 100-yard flight. This meant the shaped charge jet would form perpendicular to the armor surface almost every time, maximizing penetration. The smooth-bore rockets were hitting with angular variations up to 45 degrees, which explained why penetration results were so inconsistent. There was also a secondary effect nobody had predicted initially. The rifled tube's grooves created a slight gas seal as the rocket accelerated. This seal meant more motor exhaust pressure pushed the rocket forward instead of escaping around it. Velocity increased by roughly 8% from 280 ft/s to just over 300. That extra velocity translated to harder impact force and slightly better penetration even before the shaped charge detonated. So the promise was this. Rifling would deliver consistent nose-first impacts at higher velocity, which would generate perfectly formed shaped charge jets hitting perpendicular to armor, which should in theory produce 8 in penetration depth at 50 yards. That's double what smooth-bore bazookas achieved on their best shots. And more importantly, it would be consistent. Every shot, same result. Theory is beautiful. Testing is where theories go to die. January 28, 1943 came in cold at Aberdeen Proving Ground. Temperature at 600 hours, 18 degrees F with wind gusts hitting 20 mph off the Chesapeake Bay. The kind of cold that makes metal burn your hands and turns breath into fog. Not ideal conditions for testing experimental weapons, but the Sicily invasion was scheduled for summer. And if these rifled bazookas were going to ship with the assault forces, testing couldn't wait for better weather. The test range setup was simple and brutal. 200 wide downrange, engineers had mounted 10 captured German armor plates on wooden frames, actual Panzer IV hull sections seized in North Africa. Each plate measured 8 mm thick, the standard frontal armor that was shrugging off most Allied anti-tank weapons. Behind each plate, they'd positioned clay blocks to capture the shaped charge jet and measure penetration depth. Beside the armor plate stood standard steel plates in graduated thicknesses, 4 in, 5 in, 6 in, 7 in, 8 in. These would determine maximum penetration capability. The observation bunker held 15 officers and engineers, including Colonel Crozier, General Barnes, Captain Skinner, and Henry Mohaupt. Protocol required official witnesses for any test that might alter approved ordnance. Several Aberdeen ballistic specialists attended to verify measurements. A stenographer recorded everything. The atmosphere, according to Skinner's later account, was tense enough to snap. The test protocol was straightforward. 20 shots with standard M1 smoothbore bazookas at 50 yards, followed by 20 shots with Mohaupt's rifled prototypes at the same range. 3 different operators for each weapon type to eliminate shooter skill bias. Targets would be measured after each FIVOT group. Hit rate, penetration depth, and jet formation quality would all be documented. First up, the smooth bore baseline. The operator, a sergeant from the Aberdeen Test Detachment, shouldered the standard M1, aimed at the first panzer plate and fired. The rocket left the tube with the familiar whoosh, trailing white smoke. It hit the plate 2 FT left of center with a sharp crack. Engineers downrange examined the impact. Penetration depth of 3.8 in into the backing clay. Decent but not enough to reach a panzer's crew compartment. Shot 2, 4.1 in. Shot 3 missed the plate entirely, sailing wide right. Exactly the accuracy problem that made this test necessary. Shot 4, 3.5 in. Shot 5, 4.4 in. The pattern emerging was inconsistency. Even when the rockets hit, penetration varied by nearly an inch based on impact angle and jet formation quality. By shot 15 of the smooth bore group, the results were clear. 11 hits out of 15 attempts, penetration ranging from 3.2 to 4.6 in, average around 3.9 in. The 4 misses at 50 yards, point-blank tank killing range spoke volumes. One rocket had tumbled so badly it hit the plate sideways and failed to detonate properly. These numbers matched field test data. They also confirmed what everyone already knew. The smooth bore bazooka was marginally effective at best. The rifled prototypes came next. Mohaupt had fabricated 3 tubes with spiral grooves cut at a 1 in 6 twist rate, 1 complete rotation every 16 in of tube length. The grooves were shallow, only 30,000 of an inch deep, just enough to grip the rocket body and impart spin without creating excessive friction. First rifled shot, dead center hit, penetration 7.2 in. The engineers downrange called out the measurement and the observation bunker went quiet. Second shot, 7.4 in. Third shot, 6.9 in. Fu asked for the test to pause while engineers verified the measurement methodology. They remeasured every rifled impact. The numbers held. Testing resumed. Shot 15 with the rifled bazooka hit the thickest test plate. 8 in of rolled homogeneous armor, the equivalent of Tiger 1 glasses protection. The rocket struck dead center, detonated, and sent a spray of molten metal through the observation slit in the test bunker 300 wide away. The downrange crew waited 30 seconds for the plate to cool enough to approach, then called back the measurement. Complete penetration. The shaped charge jet had burned through all 8 in and into the clay backing behind it. Penetration depth in clay 2.3 and beyond the plate face. General Barnes stood up from his observation position. According to the official test report filed later that day, he said 5 words. Run the next 5 shots. The stenographer noted that Crozier objected, stating that sufficient data had been collected. Barnes overruled him. The test continued. Shots 16 through 20 produced results that made Aberdeen's ballistic specialists check their instruments twice. 7.88 in, 8.1 in, 7.6 in, 7.9 in, 8 in. Not a single shot penetrated less than 7.6 in. Not a single shot missed the target plate. The consistency was what shocked everyone watching. Smooth bore penetration varied by 1.4 in across 15 successful hits, a 36% variation. Rifled penetration varied by 0.5 in across 20 shots, a 6% variation. You could predict what a rifled bazooka would do. You could trust it. The observers moved downrange after the final shot to examine the armor plates up close. Every rifled impact showed the same distinctive pattern. A circular entrance hole roughly 2 in diameter, perfectly perpendicular to the plate's surface with clean edges indicating the shape charge jet had formed correctly and penetrated without deflection. The smooth bore impacts looked different. Irregular holes, some showing evidence of jet deflection or partial penetration, several showing sideways strikes where the rocket hit at an angle. Back in the observation bunker, the ballistics team compiled final numbers while everyone waited. The data was devastating to the smooth bore design. Hit probability at 50 yards, smooth bore 73%, rifled 100%. Average penetration, smooth bore 3.9 in, rifled 7.7 in. Maximum confirmed penetration, smooth bore 4.6 in, rifled 8.1 in. Consistency rating, a statistical measure of result deviation. Smooth bore failed to meet acceptable standards. Rifled exceeded all requirements. But here's the number that mattered most to infantry officers. Probability of defeating ADIM frontal armor on a Panzer IV. Smooth-bore bazooka approximately 15% accounting for both hit probability and penetration failure. Rifled bazooka 97%. A soldier with a rifled bazooka could reliably kill the most common German tank he'd face. A soldier with a smooth-bore bazooka would die trying. General Barnes convened an immediate decision meeting in Aberdeen's headquarters building. Present Crozier Skinner, Mohaupt 3 ordnance production officers and 2 logistics majors. The meeting lasted 45 minutes. The question wasn't whether to adopt rifling. The test data made that decision automatic. The question was how fast they could retrofit existing production and whether to recall bazookas already in the field. Production officers reported that rifling existing tubes would require specialized equipment, but was mechanically straightforward. Each tube would need to pass through a rifling machine. Essentially, an industrial drill with cutting heads that carved spiral grooves in a single operation. Time per tube approximately 8 minutes. Cost per tube $12 for machine time and inspection. With 3 factories running rifling operations in parallel, they could convert existing inventory in 6 weeks. The logistics officers dropped the complicated news. 14,000 M1 bazookas had been manufactured. 8,000 were still in stateside inventory and could be rifled before shipment. 6,000 had already deployed. 3,000 to North Africa, 2,000 to the Pacific Theater, 1,000 to training bases in England. Recalling deployed weapons for modification would create a gap where frontline units would have no anti-tank capability for 2 to 3 months, while weapons shipped back got modified and shipped forward again. Barnes made the call within minutes. Rifle everything in stateside inventory immediately. Begin manufacturing new tubes with rifling already cut and develop a field modification kit for deployed weapons. The first rifled bazookas reached combat units in April 1943, just in time for Tunisia. The 1st Armored Division received 200 modified M1A1 launchers, the new designation for rifle tubes during the final push against German forces near Bizerte. Staff Sergeant Julius River's after-action report from April 23 described an engagement that would have been impossible 3 months earlier. His team engaged a Panzer IV at 70 yards, fired once, and watched the tank brew up as the crew bilayed out. First shot, total kill. He wrote that his men couldn't believe the damn thing actually worked like they promised. By June, production had shifted entirely to rifled models. The M9 rocket launcher, an improved version with better sights and a 2-piece tube for easier transport, started rolling off assembly lines with rifling standard. These were the weapons that landed at Salerno in September 1943, where the 36th Infantry Division used them to break up German panzer counterattacks on the beachhead. Lieutenant Colonel William Darby's Ranger battalions reported bazooka teams accounting for 11 confirmed tank kills during the first 3 days of fighting. Anzio, in January 1944, provided the real stress test. German forces threw everything at the Allied beachhead, including Tiger the Firmer's heavy tanks that earlier bazookas couldn't scratch. But the M9's aid and penetration capability meant even Tigers were vulnerable if you hit the side armor or rear deck. Private First Class James Arnes, yes, the future Gunsmoke actor, served as a bazooka gunner at Anzio and later described stalking a Tiger through rubble. You knew if you got the shot off clean, you'd kill it. That confidence kept you alive because you weren't panicking, just working. D-Day, June 6, 1944. Every American infantry company that hit Utah and Omaha beaches carried at least 4 bazooka teams. The weapons proved essential not just against armor, but against fortified German positions where the shaped charge jet could blow through concrete gun emplacements. After-action reports from the 29th Infantry Division noted that bazooka teams cleared 12 pillboxes on Omaha Beach during the first 6 hours, allowing infantry to push inland. The real proving ground came during Operation Cobra in late July 1944, the breakout from Normandy. American infantry divisions advancing through hedgerow country ran into German armor ambushes constantly. This was exactly the scenario bazookas were designed for close-range surprise engagements, where portability and first-shot effectiveness mattered more than tank gun range. The 4th Infantry Division logged 37 confirmed armor kills with bazookas during Cobra's first week. Tank destroyers and Shermans got most of the credit in official reports, but infantry journals tell a different story. Bazooka teams often killed German tanks before friendly armor even arrived. The Ardennes Offensive in December 1944, the Battle of the Bulge, tested everything. German Panther and Tiger tanks smashed through American lines in fog and snow. Isolated infantry units found themselves defending crossroads and towns with bazookas as their primary anti-tank weapon. At Bastogne, the 101st Airborne used M9 launchers to knock out at least 18 German tanks during the siege. Captain James O'Neill, a company commander with the 5,002nd Parachute Infantry, reported his men ambushing a Panther column on December 22nd, killing 3 tanks in under 2 minutes by hitting them from building positions at 30 yards. The consistency made all the difference. Soldiers learned they could aim a rifled bazooka like a rifle. Point, squeeze, hit what you pointed at. Technical Sergeant Forrest Guth, who fought from Normandy to the Rhine, explained it simply in a 1945 interview. Before rifling, you fired and hoped. After rifling, you fired and knew. By the time American forces crossed the Rhine in March 1945, bazookas had accounted for over 800 confirmed German armor kills in the European theater. That 800 number tells only part of the story. The real revolution happened in how armies thought about infantry anti-armor weapons. Before rifled bazookas, portable rocket launchers were experimental gear that might work under ideal conditions. After Aberdeen's January 1943 test, they became primary weapons that infantry commanders built tactics around. And every rocket weapon America developed afterward started with one assumption: the tube will be rifled. The 3.5 and M20 Super Bazooka that appeared in 1945 came with rifling machined directly into the tube during manufacture. This weapon could penetrate 11 in of armor, enough to threaten even King Tiger tanks from the side. When North Korean T-34 tanks crossed the 38th parallel in June 1950, American infantry units stopped them with M20s, weapons that existed because Mohaupt convinced skeptical officers that spinning rockets was worth the risk 7 years earlier. Korea proved rifling's value in ways World War II never did. The terrain, mountains, narrow valleys, urban fighting meant tanks and infantry fought at ranges under 100 yards constantly. The M20's accuracy let a 2-man team engage armor from protected positions with confidence. After-action reports from the Busan perimeter fighting in August 1950 show bazooka teams accounting for 41 T-34 kills in 2 weeks. First Lieutenant Ernest Schoenfeld's platoon knocked out 7 tanks in a single day near Taegu using tactics that depth.